Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about a module, some earlier attempts towards quantum mechanical concepts 1 under the paper Quantum Mechanics 1. So students, let us see what we are going to learn in this module. Firstly, we learn a few basic processes which show how interaction of the electromagnetic waves with matter can be visualized to occur by means of elementary processes in which the radiation appears to be composed of discrete quanta of energy called photons. Secondly, know that the energy E and the momentum P of a photon are related to the wave characteristics like the frequency mu and the wave number k by the relations E is equal to h mu and vector P is equal to h cross vector k, where h is the Planck's constant and h cross is equal to h by 2 pi. Thirdly, we learn the concept of wave-particle duality by analyzing the Young's double-slit interference experiment. And finally, know that 1. Light behaves simultaneously as a wave and as a stream of independent photons. Secondly, the possibility of explaining interference fringes due to interaction of photons is ruled out. And thirdly, the wave nature of photons makes it impossible to detect through which slit a photon has passed to produce the interference fringes. It is only to enable us to determine the probability of striking the screen at a point. Now, coming to the subject of quantum mechanics. Quantum mechanics provides a mathematical description to understand the phenomena which occurs on a microscopic, that is, atomic or subatomic scale. In fact, the subject grew as a result of culmination of new and path-breaking ideas introduced to account for the observed phenomena which could not be explained on the basis of classical concepts. This module and the one that will follow it present a review of some of the basic concepts and ideas which lay the groundwork for a systematic development of the subject. So, to begin with, why quantum mechanics? The reason is that there were a number of phenomena that happened at the turn of the last century or which were discovered at the turn of the last century for which the classical theories were grossly inadequate to explain them. They were primarily the black body radiation, that is, the classical theories failed to explain the energy density distribution of the black body radiation. The second phenomena was the photoelectric effect. The wave nature of light could not explain the photoelectric effect, and then came the Compton effect. The Compton effect was an effect in which the wave theory of light just could not offer any explanation. And finally, the wave-particle duality, which everybody had to reconcile to, and which was also demonstrated by the Young's double-slit experiment. Black body radiation, light quanta, and the Planck-Einstein relation. One of the earliest phenomena not explained by the electromagnetic theory and the other classical theories was the nature of the energy spectrum of black body radiation. Before we go on to that, we first need to understand what is black body radiation and what is the best way of practically realizing a black body spectrum. As you know, a black body, by definition, is one which absorbs all the radiation it receives and does not reflect any. Such objects are perfect absorbers as well as emitters. So, the best way to realize a black body is by making a hollow enclosure with a small opening, such as an oven. And this kind of a setup is the best way to practically realize a black body. Such a cavity with a small aperture through which radiation from outside may be admitted contains radiations emitted by the walls of the enclosure. Now, we can look at the figure to see what were the explanations given by the classical theory for black body radiation and how these theories were inadequate to explain the complete spectrum of black body radiation. As we can see in the figure, the plot of energy density distribution at different absolute temperatures as a function of wavelength. Now, if we look at this figure, what we see is that all the earlier attempts to explain the entire energy density distribution of the blackbody radiation could not completely explain this entire spectrum. In fact, the earlier theories could only explain part of this entire energy distribution spectrum. One of the attempts to explain this energy density distribution was the Wien's displacement law. Wien's semi-empirical formula for black-body radiation agreed only for short wavelengths limit or high frequency, that is, high energy. The law stated that black-body radiation curve for different temperatures peaks at a wavelength inversely proportional to the temperature. However, this law could only explain the short wavelengths limit, that is, the initial part of the energy density distribution curve. However, as the wavelengths increased, the Wien's law was inadequate to explain the entire spectrum. Similarly, another attempt at explaining this spectrum was made by the law given by Rayleigh and Jeans, who used classical reasoning to explain black body radiation. This reasoning could adequately explain the energy density distribution at high wavelengths, but completely failed to give proper explanation for the low wavelength range, that is, high frequency range. Hence, this formula or this law was also not enough to explain the complete spectrum of black body radiation. The relationship that Rayleigh and Jeans deduced from the classical reasoning is given by E as a function of mu, d mu is equal to 8 pi mu square by c cube into k t d mu. This is the relation in terms of the frequency of the energy density distribution. This relation can also be expressed in terms of the wavelength, that is, the energy density distribution can also be written in terms of the wavelength, which is given as E as a function of lambda d lambda is equal to 8 pi lambda to the power 4 kt into d lambda. Here, if we look at the relation of the energy density distribution with respect to the frequency, we see that the term 8 pi mu square by c cube is the number of the electromagnetic oscillators per unit volume at frequency mu, and the term kBt is the average energy of the oscillators in thermal equilibrium at temperature T and is given by kT, where half kT is the contribution due to the kinetic energy term and half kT is due to the potential energy of the oscillator, and kT represents the total average energy of the harmonic oscillator. Now, if we look at the expression given by Rayleigh and Jeans and try to see what was wrong with it, then we can clearly see that in the high energy or frequency limit, that is, low wavelength limit, the expression for the energy density distribution diverges. So you can see that the term 8 pi mu square by c cube, in that term, if mu tends to infinity, then the entire expression also tends to infinity. However, if you look at the energy density distribution curve, you see that even in the large frequency limit, that is, the short wavelength limit, the distribution function is not diverging. Thus, this theory given by Rayleigh and Jeans kind of proved to be inadequate, and this particular phenomena that for high frequency the energy distribution function diverges was called as the ultraviolet catastrophe. Planck's hypothesis of energy quantization and his explanation for the entire spectrum of black body radiation. To explain the observed features of the black body spectrum, Planck suggested that the emission and absorption of electromagnetic radiation by matter takes place in discrete quanta of energy. That is, that the absorption and emission of energy by matter is not continuous but is discrete. So, if the frequency of the electromagnetic wave is mu, then the possible energies which can either be absorbed or emitted by matter are integral multiples of the quantum of energy, that is, epsilon is equal to h mu, where h mu is actually the electromagnetic oscillator energy. So the expression that Planck derived using this suggestion, or rather using this theory that he proposed, was E as a function of mu is equal to 8 pi mu square by c cube into h mu upon bracket open exponential within bracket h mu by kBt minus 1 bracket closed. This is the expression for energy that Planck gave. Here again we can see that the number density for the harmonic oscillator is given by 8 pi mu square by c cube, but instead of the average energy being taken as kT that was done in the classical theory, here the energy is taken as h mu upon exponential within brackets h mu by kBt minus 1. In this manner, Planck was able to explain the entire spectrum of black body radiation, and this was the first success of the quantum theory. Photoelectric effect. So in this module, we'll discuss the photoelectric effect. But before we go on to discussing the photoelectric effect, we first need to know what was the basis of this effect. So Hertz demonstrated experimentally the electromagnetic nature of light waves, and this led to what is now known as the photoelectric effect. So firstly, what is photoelectric effect? Photoelectric effect is basically a phenomena in which the photoelectrons are emitted from a metal surface when a light wave is incident on it. And there are three very important characteristic features of this effect. First, that the number of photoelectrons that is emitted, which is also the photoelectron current, is proportional to the intensity of light. Second, that the energy of the photoelectrons emitted is directly proportional to the frequency of light. And finally, the time elapsed between the striking of the light wave to the metal surface and the emission of the photoelectron is hardly there. In fact, it's almost an instantaneous process, which means that the time lag is less than 10 to the power minus 8 seconds. However, these three important points about the photoelectric effect could not be explained by any of the classical theories. Most importantly, that the wave nature of light alone could not explain any of these points conclusively and convincingly. Thus, in 1905, Einstein showed how the phenomena of photoelectric effect, hitherto unexplained by classical theory, could be described in a simple way by considering a monochromatic beam of light not as waves but as bundles of light quanta of energy, h mu. Secondly, Einstein applied Planck's hypothesis and proposed that when a beam of light of frequency mu is incident on the metal, it takes a certain amount of minimum energy called the wave function, that is, W is equal to h mu naught, where mu naught is the threshold frequency to remove the electron from the metal surface. When the incident frequency mu, that is the frequency of the light wave, is greater than this threshold frequency mu naught, which is a characteristic of the metal, the ejected electron has a kinetic energy Ke given by Ke is equal to h mu minus W, where W, as defined above, is the work function of the metal surface and is found to vary linearly with the frequency of the incident radiation. But in contrast to the wave picture of light, it is independent of the intensity of light. Now, coming on to the second effect, which again demonstrates the particle nature of light, is the Compton effect. In 1924, Arthur Compton discovered that when hard X-rays of shorter wavelengths, which means high energy or high frequency, are scattered by atoms of an element of low atomic number, such as graphite, the scattered radiation contains not only the original wavelength but also softer X-rays of longer wavelength. He explained this phenomena by assuming that X-rays consist of a collection of photons which characterized the energy E and the momentum P. These photons are basically energy particles, and when one of these quanta of energy E hits a free or a loosely bound electron, it would recoil. So this can also be visualized as that you have a billiard ball which is at rest, and another billiard ball comes and hits this billiard ball which is at rest, and it's an elastic collision between two particles. In a similar manner, here you have a photon which is moving and an electron which is at rest. This photon comes and hits the electron and gets deflected, and the electron, because of this collision, also starts moving, and the collision on the whole is completely elastic. As a result, it would have an energy E prime less than E, that is, the energy of the incident photon is more than the energy of the deflected or the scattered photon, where E prime is the energy of the scattered photon and E is the energy of the incident photon. And after the collision, also the corresponding wavelength of the scattered photon, lambda prime, is greater than the wavelength of the incident photon, which is lambda. If we look at the figure which depicts the Compton effect and define the photon which is incident on the stationary electron to have an initial energy E and initial momentum P0. This photon hits the electron and there is an elastic collision. Due to this elastic collision, the photon gets scattered at an angle theta with respect to the original direction in which the incident photon was moving. The momentum of the scattered photon is P1. The free electron, which was initially at rest before the collision happened, now starts moving with a momentum P2 at an angle phi with respect to the direction of the incident photon. Compton derived the expression for the change in the wavelength of the photon by considering this entire process as an elastic collision and using the equations of conservation of energy and momentum. The mathematics that he did led him to the relation delta lambda is equal to lambda 1 minus lambda naught, which is equal to h by mc into 1 minus cos theta. In this equation, lambda 1 is the final wavelength, lambda naught is the initial wavelength, and the expression h by mc into 1 minus cos theta does not contain any term of the wavelength. This means that the change in wavelength is independent of the initial wavelength of the incident photon. Also, this relation comes out to be positive because h, the mass, and the speed of light c, where h is the Planck's constant, all these three terms are positive, and the maximum value that cos theta can take is 1. Thus, since the change in wavelength can at best be 0 or is generally positive, means that the energy of the scattered photon will always be less than the energy of the incident photon, because part of that energy is transferred to the electron, which starts moving. Wave-particle duality. Light, in fact, exhibits a dual nature, that is, it exhibits a wave nature as well as a particle nature. The particle nature of light is amply demonstrated by both the photoelectric effect as well as the Compton effect. The big question then arises, what is light? Is it a particle or a wave? The answer to this is that it is both. When light is moving, it moves as a wave, but when it interacts with matter, it interacts as a particle, thus demonstrating both the aspects simultaneously. If we look at this figure, which shows the Young's double slit experiment, we see that the incident light passes through either of the two slits S1 or S2 and then hits the screen D. When this D screen is analyzed, that is, supposing if this screen D is a photographic plate and the pattern that the light leaves on the screen is analyzed, it is seen that it is an interference pattern. Interference is inherently due to the wave nature of light. However, how does one know that which of these two slits, that is S1 and S2, was the slit from which the photons went by? This is extremely difficult, or rather impossible to determine. But the photons of light pass through either of the two slits and then finally reach the plate D to give us an interference pattern. Inferences from the experiment of Young's double slit. Light behaves simultaneously as a wave and as a stream of independent photons. The wave nature, which appears to be an inherent property of photon, enables us to calculate the probability of the manifestation of a photon. The probability amplitude of a photon appearing at time t at the point r can be described by the electromagnetic wave represented by E vector r and t, that is, the electric field as a function of the vector r and t, and the corresponding probability is proportional to the modulus, the square of the modulus of E as a function of vector r and t. Here E as a function of vector r and t is actually the sum of the individual electric fields associated with the photon emerging either from slit S1 or slit S2, and the intensity of the light is proportional to the square of the modulus of the sum of these two fields. So students, let us summarize what we have learnt in this module. The phenomena of blackbody radiation, photoelectric effect, and Compton scattering demonstrate the particle nature of the electromagnetic waves, and that the interaction of the electromagnetic wave with matter occurs through elementary processes where the radiation appears to be composed of energy particles which are called photons. The energy E and its momentum P are related to the wave characteristics of the photon or the electromagnetic radiation, where frequency mu and the wave vector k are directly related to these two quantities. The energy E is equal to h mu or h cross omega, where h is the Planck's constant, omega is the angular frequency, mu is the frequency of the electromagnetic radiation, and h cross is h by 2 pi, while the momentum of the electromagnetic wave is related to the wave vector k through the relation p vector is equal to h cross k. The concept of wave-particle duality through Young's double slit experiment to demonstrate that 1. Light behaves simultaneously as a wave and as a stream of photons. The wave nature appears to be an inherent property of the photon, enabling us to calculate the probability of the manifestation of the photon. Second, the probability amplitude of the photon appearing at a time t at the point r can be described by the electromagnetic wave represented by E as a function of r and t, and the corresponding probability is proportional to the square of the modulus of the amplitude of E as a function of r and t. Thank you.